Mercury is the closest planet to the Sun, yet it remains one of the most mysterious worlds in our solar system. In fact, despite decades of space exploration, only 2 missions have ever reached Mercury Mariner 10 in 1974 and Messenger in 2011, with just one more BepiColombo scheduled to arrive in 2025. This limited attention might seem strange at first. After all, Mercury is right next door, isn't it? But visiting Mercury is not like taking a short trip across the solar system. Its proximity to the Sun creates enormous challenges, both for spacecraft and for scientists trying to study it. Of these rare missions, only one messenger managed to orbit Mercury and send back a treasure trove of detailed images. These close-up glimpses revealed a surface scarred by ancient impacts, shaped by deep internal processes and marked by features that are still puzzling scientists today. Some of what we see hints at the raw, violent power of the early solar system. Other features remain unsolved mysteries still debated more than a decade after Messenger's discoveries. Today, let's take a journey across Mercury's surface. Together, we'll examine the strange formations revealed by Messenger's cameras, unravel what they tell us about the planet's history, and explore why Mercury, though often overlooked, holds some of the most fascinating secrets in the solar system. By the end of this episode, perhaps you'll agree that this small world deserves much more attention. When we look at Mercury, a few features immediately catch the eye. The first is its colour. Many imagine Mercury as a dull grey world, much like our moon, but in reality, its surface is speckled with subtle shades of grey, beige, and cream, with lighter streaks crisscrossing darker planes. Scientists believe these darker areas contain high levels of graphite, the same material found in pencil leads. Imagine then an entire planet sprinkled with the stuff we use to write with. Meanwhile, the lighter patches remain a subject of study, hinting at different compositions or geological processes we'll return to later. Beyond colour, the most obvious feature is craters. Mercury's surface, like the Moon's, is covered with them. Billions of years of cosmic debris rain down on this unprotected world, carving out scars across nearly every region. But there is more to these craters than just impact history. The sharpness of a crater's rim tells us something about its age. A sharp, crisp crater suggests a relatively recent impact, while older craters appear worn, their rims softened by time, and sometimes new impacts land right on top of older ones, creating overlapping features that serve as a timeline written into the rock. What's fascinating is what these differences imply. Even though Mercury has no substantial atmosphere and no weather as we know it, the planet's surface is not entirely static. Over geological timescales, processes beneath the crust and the sheer force of impacts have reshaped its face. When we examine these craters, we aren't just looking at scars, we are seeing a record of Mercury's violent past, a glimpse into an ancient era when the solar system itself was still settling into order. As we scan across Mercury's surface, another strange feature appears: ridges and cliffs that stretch for hundreds of kilometres, cutting across craters and plains alike. At first glance, they resemble the folds of crumpled paper. These formations, called lobate scarps, tell us something remarkable about Mercury's history. Scientists believe that in the past Mercury's core was much hotter. As it cooled over billions of years, the planet contracted. Think of a grape shriveling into a raisin, its skin buckles and folds. In the same way, Mercury's crust crumpled as the planet shrank, leaving behind massive ridges that still scar its surface today. This shrinking process is unique compared to our moon, which lacks the same extensive network of folds. It shows that Mercury has a dynamic interior history, a story written in cliffs and scarps. But contraction isn't the only process at work. Some craters reveal another phenomenon: slumping. In one crater, for example, part of the rim collapsed inward, sliding into the basin below, while the rest of the rim remained intact. Why only part of it gave way is still a mystery. Was the soil composition uneven? Did the angle of the impact play a role? We don't yet know. What we can say is that Mercury is not a frozen, unchanging world. Its crust continues to bear evidence of forces that once bent and reshaped it in ways we are only beginning to understand. Among the most striking features on Mercury are the enormous ray system's spidery lines that radiate outward from certain craters. These bright streaks stretch for hundreds, and in some cases thousands of kilometres across the surface. Why are they brighter? Because the material blasted out from beneath Mercury's surface has a different composition than the weathered graphite-rich surface layer. Fresh debris untouched by solar radiation creates these pale rays that stand out starkly against the darker planes. For years, scientists puzzled over how such patterns formed. In laboratory experiments, no matter what speed, angle or size they used to simulate impacts, the debris always landed in neat circular patterns, not in long, thin streaks. The breakthrough came, surprisingly, from students. In 2018, researcher Tapan Sabawala noticed that a group of students who hadn't bothered to smooth the sand in their experiment managed to reproduce ray-like streaks. The rough surface was the key. On uneven terrain, the ejecta didn't fall in perfect circles. It spread in branching, spider-like patterns. Sometimes science advances not through meticulous planning, but through happy accidents. And in this case, it helped unlock one of Mercury's greatest mysteries. The scale of these ray systems is staggering. The crater Hokusai, for example, has rays so vast they nearly encircle the planet, stretching across much of its 15,000 kilometre circumference. Another crater, Debussy, boasts rays over 1,000 kilometres long. While the Moon also has ray systems, Mercury's are larger and more prominent. They remind us of the incredible violence of Mercury's past. So close to the Sun, any asteroid or comet pulled into the inner solar system would have struck Mercury with immense force, far greater than Mercury's gravity alone could provide. These rays are not just scars. They are monuments to a time when the solar system was a shooting gallery, and Mercury, small and vulnerable, took the brunt of the fire. As fascinating as Mercury is, it's also one of the hardest places to reach. The Sun's enormous gravity dominates this region of space. For most objects, the Sun's pull simply overwhelms Mercury's weaker gravity, making it nearly impossible for the planet to capture moons or passing bodies. This is also why spacecraft find Mercury so difficult to approach. Any probe heading toward Mercury must fight not only the pull of the planet itself, but the relentless gravity of the Sun. Instead of gently falling into orbit, a spacecraft must carefully brake maneuver and block its way into position. This is part of the reason why only a handful of missions have ever succeeded. Visiting Mercury is not just a journey across distance, it's a struggle against the most powerful gravitational force in the solar system. Among Mercury's many craters, one formation stands out as particularly strange: Apollodorus and the surrounding system of fractures known as Pantheon Fossae. At first glance, Apollodorus seems like just another crater, but radiating outward are dozens of fractures resembling the shattered lines of broken glass. This is unusual. Mercury's crust usually reacts to impacts by creating circular craters or ray systems, not by fracturing like brittle material. The mystery deepens when we notice that Apollodorus is not perfectly centered in this web of cracks. The crater lies slightly off to the side. That suggests Apollodorus might not even be responsible for the fractures. Perhaps the cracks were already there, formed by some other process, and later an asteroid struck nearby, leaving the crater we see today. If so, what caused Pantheon Fossae? One possibility is internal activity. Instead of something striking from above, perhaps forces beneath Mercury's crust pushed upward, cracking the surface in a radial pattern. It could be evidence of volcanic or tectonic stresses frozen in time. But here's the problem. We don't see this pattern anywhere else on Mercury? Why here and only here? Could conditions have been different, colder, harder, or more brittle at that specific moment? Or is this the one surviving clue to an ancient process that has otherwise disappeared? For now, no one knows for sure. Pantheon Fossae remains one of Mercury's greatest mysteries, a riddle etched into the rock that reminds us just how much there is left to discover. As we step back and take in the bigger picture, Mercury emerges not as a static, lifeless rock, but as a world with a dynamic past. Its surface bears the marks of contraction, collapse, and cataclysmic impacts. It is a planet shaped by both internal forces and external bombardments, with features that still defy explanation. Every wrinkle, every ray, every fracture tells part of the story of the solar system's violent youth, and although Mercury may not have oceans, atmospheres, or the promise of life, it holds something equally precious, a record of the solar system's earliest days. So, as BepiColombo approaches Mercury in the coming years, perhaps we'll finally answer some of these questions, or perhaps we'll uncover new mysteries that challenge our understanding even further. For now, Mercury remains the forgotten world, but also one of the most fascinating.